classroom. Tonight, in a night stream, I figured let's look at some more interesting graphs. These interesting graphs are going to be a particular new type of function, you could say, or sort of an effect we could have within our graphs. And what that's going to be is the ability to round numbers, which I realized as I was playing around with this is a very poorly named thing, because rounding a number to the nearest integer or nearest whole number, where, if I'm at something 0.4, I would go down to that 0.0, something 0.6 would go up. 0.5 typically is treated as rounding up, and anything between that and point infinite nines, essentially. Although point infinite nines, we could argue, is already there, already rounded, just expressed differently. Now, it's a poorly named thing because rounding a graph actually makes it much less round in many cases. If I took the equation for something like a circle and I throw a couple roundings at different points, the circle is far less round under most definitions of roundness when we're not talking about round to the nearest whole number. And I was playing around briefly on my own and found that when we combine some of the trig or trigonometric functions, like sines and cosines and secants and tangents and such, that they combine interestingly with rounding things because they have quite a lot of behavior, including a lot of curved sections, that now we'll see become far less round when we apply the rounding to them. I might need to make a short about a clear example just using a circle, the best example we find today, of how this can make things less round. Now, just to be clear about how this looks on a graph, let me pull open the graph software here. We're using just the website Desmos's free graphing calculator for now, and it's 2D, although we can try their demo of their 3D thing, like their beta version of that. So if we find any particularly cool things here, we could throw a Z in as well for another axis. Now, what we will be doing today is beginning with a reminder of what it looks like to round a function, or to round a number, but now we are going to be looking at a function that's rounded. Now, first just try and imagine in your head each of these as I say them before I type them, because when I type them, they appear. And it's a good little mental challenge if you can try and picture these before I make them. What would it look like if I say y is x rounded? Or the way we're going to write that is y is rounding each x to the nearest integer. Here we can see that at the 0.5 marks, they go toward 1. Same with below the next 0.5 mark. Afterwards, we jump higher. So what about rounding x squared? What do you think that'll look like? Well, now we have this sort of glitchy version of a parabola. What about if we round the equation for a circle? Well, there's sort of two ways we could do this. Or there's a few ways, many ways we could do this. But a few that come to mind are the circle equation can typically be phrased as x squared plus y squared. And I'm leaving them separate for now because we may want to manipulate them together or separate, equals some radius, which is a. Now, if you look at this a certain way, you could see a being on a slider as like we're looking through cross sections of a 3D graph of a sphere, almost. See that sphere getting bigger and smaller, like as you cut through the slices of it? This is sort of like the end of the orange where it's mostly rind. Here's a nice bite in the middle of the orange, Now, what happens if I round some of these? Well, if I round them separately, we get this at the right times. We need them to be at the right zones, it appears, when a is 2.8. Unless they're just having too much trouble displaying anything, there appears to not be anything. However, when a is 3, we can see this glitchy circle. And this is the type of thing I might have to show in a short. How come we call it the rounding function, or rounding a number in general, when it makes things less round? Now, what'll be different if we round them together? If I have x squared plus y squared in a single rounding? Well, in this case, didn't end up messing with it. At level 3 at least. It makes the circle vanish at certain points. It's like, if we're at the right spot, we get the right circle. The wrong spot, we get nothing. Now, those were the two ways I mentioned, but of course, as soon as I said there are two main ways we could do this, I sort of realized another type of way, which is, what if we round x and then square that? And like we do the squareds outside. Round of x squared plus round, the same thing but y. And this one is not likened to exist. This one, not a big fan of existing. Oh, wait a minute. At the right zones, we get something. Here we get a bracketed version of a square with some holes missing. That's when a is 2. Do we get anything when a is 3? Don't see anything. But what about when a is 1? We get this thing. Well, that's pretty neat. That's the bit that took some of the pieces from the square. Look, these bracketed things, it's like, what are they missing? Whoa, there's another one. But these ones, it seemed almost to line up with those bits at the edge are like, what's missing here? Now, oh, and there's a square. We have to be at 0 for there to be a normal square. So, that's just rounding the circle equation. Already pretty interesting because I haven't experimented with this. In fact, I'd never even considered really what it would look like to round part of a graph in that way. And so some commenter mentioned, what if we try the square root of 2? I'm not sure if I can set a to that unless I type it in. That might have been for a previous one of these. Anyways, what we're going to move on to is our good old trig functions, because when we throw things like sines and cosines in a blender together, we get cool shapes that maybe have never even been discovered or experimented with before. Let's see, like this. Has anyone ever graphed this before? Probably not. So, it didn't even do... I have the wrong parentheses or something. It was supposed to be a random example. Forgive me. Now, let's go to a classic example, which was when I use sines on the circle equation. And by classic, I don't mean like in classic math. I mean, I found this one day, and I don't know why it's not talked about more, but it's classic in the combo classroom. It's a combo classic. Now, here, if we make those a, we get these crazy shapes. And this is the point where we're going to switch from an equal sign to an inequality usually, because seeing it colored in is more fun. So this is our good old mutant one that I've shown a few times. Something that someday maybe I'll try and figure out a little deeper the math behind why exactly it's doing these things and make an episode about it. But I just know I fiddled around with stuff one day, and this was a really simple equation with pretty complex behavior. And what happens now if we round parts of that? Because today we're going to be taking things that may on their own be cool, but maybe are more common, and seeing what happens when we throw the rounding in. Now, that's putting it there, but let's put it on both to see. And thank you to everyone commenting so far. And there's someone asked about something called shader toy. I'm not sure what that is, so I don't know. But anyways, leave any comments if you have any random thoughts. And as a reminder, although we will be streaming for a while tonight, if any of you leave early, make sure you are caught up on some new bonus videos and shorts I have put out on this channel, as well as my last main episode that's linked in this description. Now, here we get something pretty interesting. This, when we round what was this circular thing, and let's compare them. Let's make a clone of it that wasn't rounded. So this is the one we had. And let's put the rounded one a little darker, or that didn't help. Here, we'll make the rounder one a bit darker in comparison. So this is a new friend to this graph I love. This combo classic now has this thing, oh, I was going to say living inside it, but it's not always inside, I guess. We can note that at least for what they're trying to do, some of these, they say it contains fine detail that's not fully resolved. What they mean by that is we're not seeing a perfect image of it, and sometimes if you zoom out, you can see it messing up. Like, this isn't what it looks like out here. It can't handle it. But we can tell visually pretty much when we're at the level where it actually is getting all the detail we need. And here we can note they do jut outside of it a little bit, at least for this value of A. But what I was going to say is what they're trying to do is have just shaded bits for when it's greater than, or when it's just greater than. If it's equal, they're going to make the line a little darker. And let's see if that's true, that none of this would appear if it was just equal. Yeah. So we would see thicker lines around sectors, which we'll see at different points, for bits that are exactly equal in this inequality. But here, that's none. And this is really cool. This actually shows that sometimes when we look at a graph with the equal sign, we're not going to see anything. But if we had been looking at it with an inequality, we would have seen something hiding there. That's pretty crazy. Let me know if you can find any other fun examples later on your own time of equations that when we have just equal, we don't see anything, but they have something really cool hiding in the inequality. Now, here we can notice, let's put this back. As we mutate this, first we have these separate squares in a grid-like thing, and they stay sort of, it seems, a minimum size. As long as they're here in the existent zone for them, it seems like the squares don't get smaller than they are right now. Or I should say rectangles, because only some of them are squares. In fact, you'll notice that the way they get smushed as they go different directions makes the squares lie on diagonals. So the ones that are perfect squares are the ones that intercept the line y equals x or y equals negative x. So going here, and of course, when I'm making these observations, maybe someday I'll seem to notice something that isn't precisely true, like the square might glitch somewhere. These graphs are quite unpredictable, and as far as I know, they haven't been studied so far, so I'm mostly making observations and things that I can deduce. These aren't things that have been proven necessarily, and I'm sure we'll find many surprises and twists as well. So getting up here, we get to a point where we have those thicker borders I was talking about. So the thicker borders are where it's exactly equal. And we get some of those for this darker graph, the one with rounding, when A is 1 here. And when we go past that, we don't have the darker borders anymore, but we have these shapes sort of cross. They build this sort of network there. And then they hit like a maximum size, it seems like. Or wait, they seem like they stopped growing for a range. It seems like between 1 and something, and not much less than 1, they've jumped. Maybe they even jumped from 1 to that. Let's put a little more sensitivity onto this and make our steps a little smaller. Wait, that didn't work. That made my steps even worse. What's going on there? Wait, why 0.02? Did I hit that? Okay. This isn't going up by 0.01. Maybe it's just not able to there for some reason. I don't know. Yeah, I don't know. Weird. So, what if I put another O? No? They just don't want to. Okay. Step 0.1. Fine. Now, as we go... Wait, but now it's 0.2. Why are they messing with me like this? Why can't I go more precise than this? Okay, there. Now, we've linked up the bridges again, but it seems like they kind of jump from being separate to being together, and then they don't grow the, like, gray bridge there between 0 and 1. Then at 0, it gets a line outside it where it's exactly equal. Then it starts going crazy, and now it's formed these reverse things. It's now blotted out everything but the shapes. We get something at -1 too, an interesting equality where we get the thicker lines. And this on its own is a pretty cool, like a wallpaper or tiling. I mean, it's not mathematically a tiling, really, but it looks tile-like. So now let's try some other experiments. And first we're going to get rid of that fella, but we may make more clones over there later if we need. Let's just try real quick what happens if we were to have multiplied these instead of adding them. Well, now we get these sort of squares in a grid. There's a lot of zones where nothing's happening and where it stays frozen between different states. And then it jumps. That looks pretty neat. Now, what were to happen if we were to subtract them instead? Okay, a lot of these are freezing in a strange way at different times. Now, if we were to add these, but mix up our trig functions, let's see what happens. Like, you know, we got tangent is always pretty crazy. If I replace these with tangent, we get this. And it looks... Now, let's go again and do the clone version that's this, but not rounded. So... we can see normally it looks sort of like this. Now what's it going to look like in our rounded version? It freezes, but then it like hits new checkpoints. It like hits checkpoints it freezes at between the integers. Each one, it grows a bit, though. Here's one at 1, where we get a clear border line. And interestingly, it does appear to be straight, but due to these straight lines getting smaller at a particular amount, we get a sort of curve to the total shape. Although if we were to go this way, it curves a different way, sort of. So this is a neat friend of our tangent version of it. It's sort of like, in this one, we can see it as like leaping as if it's trying to catch up to the line, or the line's trying to catch up to it. All right, that one was pretty cool. Now, to go forward, let's just try one or two more types of trig operations substituted real quick. Like secant is a bit different. And let's zoom out a bit. Whoa. Ooh, these ones are interesting, and it keeps doing that glitchy thing with the way we have it set up. But that's okay. Now let's try some new experiments. And to make this a little simpler for our experiments, let's put all of the stuff in one rounded thing for now. And we had been playing around with squares of these. Let's see what happens when we try raising them to different powers, like what if x goes to y, and maybe we add y going to x. Now, we get this tiny little blip right there. And we get this curvy thing. What's up with the blip? Does the blip grow or change? Well, it's freezing. Here the blip's gone. There it appears. And there the blip has an edge. But the blip sort of doesn't change size when it's there. It just exists. I wonder what we could say about this thing's area or any points it passes through. Someone said here to remove the interval restriction. We can't remove it because they have to have some sort of interval. Or make it -1 to 1. Maybe for some things, but -1 to 1 will be a little limited for some things we'll be able to see. But good suggestion still. And love all of our graph fans in the comments and whoever's watching live. Nice to have you here tonight. So, to try, well, okay, real quick, let's separate them. Let's see what happens if I were to have rounded these separately. Uh-oh, wrong types of parentheses. Okay. So what's going on here? Whoa, this is jutting out at a strange point. I wonder what we can say about that coordinate. What's going on at that coordinate? Now, oh, this is interesting. It's forming these, like, spiky things. And it seems like it's trying to approach something round, but never quite getting there. And at this zone, it is pretty boring. Alright, so let's now try seeing what happens when... This is simple exponents. What happens if I try some weirder exponents? Let's see what happens. Oops. If we do x to the ay as a changes over here. And in fact, let's have some x and y involved in this side as well. Let's just multiply an x and a y in there. Ooh, we get these spiky fern-like things. And they're growing. And they took over. This is when they just looked like grass. This is when they looked like ferns, and they took over. Well, they kind of took over. They now have negative space that looked like them. All right. And here, let's go and try, instead of just that, well, let's try this. What if I do... I want x to the y and y to the x somehow involved to see what sorts of weird symmetry that gives us. And although this will break some symmetry, what if we put 1 in the denominator? So, not doing anything, but we're at a pretty low value of a. So, let's see what happens up here. And... oh, I thought that was all of it, but you gotta zoom out sometimes. So we have these things. Here is the moment they separate. Or form together, depending what direction you're looking. So, let's try some other combinations. And one type of thing we could try is, we've done modular arithmetic as a function before. We could say like x in mod y. I've made some videos about modular arithmetic on my combo class channel if you want to learn about it later, but you could also just go along for the ride for now. Basically, this is an example of a glitchy thing that happens when we do mods. What sort of glitchiness will we get if we have... Well, first of all, let's inequality it. And then what sorts of glitchiness will we have when we throw a round in there? So now we get these spikes that are sort of hopping away one step at a time. In this case, it seems like the rounding, sometimes when I just have a single one of them, is sort of retaining some shapes of the original graph, but just making it jumpier. So maybe we want to have more than one round. Maybe we want rounded x mod y plus rounded y mod x. And yep, what did I know? We found something more interesting. Here we get these strange, almost, these ones look sort of like stalactites or something. Or this is like some upside down Batman thing or spiky mountain. And we get some strange patterns here. Look at these little missing ones. And as we evolve it, we get some crazy glitches. Often when A is 1 is when we get the equalization. But the inequalities reveal a lot. Now, if I were to have multiplied this instead of added it, we would have gotten this. Okay, one or two more mod experiments. This is if I put an A there instead. And here is if I, what if I put an A there too? Well, now I just got, whoa. What's going on here? Are they just really tiny? Yeah, and more square-like. And they grow. Here, it's like getting cut off in exact tens because I'm set to 10. If I set it to 9, they're getting like cut off at 9s. Or let's see, here's 8. 8. But wait, only the first one gets cut off there. The next one is smaller. It's not twice 8. So something's going on related to the first repetition, though. This square right here is 8. So now let's see. The mod ones are cool, but they're kind of doing a lot for the sake of what we're looking for here, because they give us double glitchiness. It's already going to look kind of glitchy with just the rounding, it seems. So we're going to mostly be mixing it with strange combos of the trig functions. That is what I put in the title, and that is what I think will be the most interesting combination. So I found it might be most interesting when we have them separate, like 2 different bits rounded. Or how about this? Let's try having the equation have a round on each side and an x and a y on each side. What does it look like if we just round x to the y and y to the x? Oh, that's the same, x to the y. Here are the spots on the graph. See, now we're getting to ones that, although they look a little less trippy, we can sort of visualize what they're actually doing. Here is where x to the y rounded is at least as big as y to the x rounded. So that's interesting. What happens if I were to have flipped this inequality? We get that. Now, what if we were to have rounded the sine of x to the y compared to the sine of y to the x? And this one's pretty wacky. We got some crab claws or something. And yeah, look at this crab. This is totally a crab. This is a crab with a lot of pinchers. Look at all them pinchers. Wait, no, that's not a crab. The pinchers got separated. So like a whole school of krill or something. Yeah, look at all those shrimp or something. Okay, I thought it was a crab. Turned out to be shrimp. You never know. So, in fact, yeah, look at this. What I thought this was a claw that looked connected to it. Not connected. So, now let's try a similar thing, but with some other of the operations. This doesn't have an A, so we're just going to have one value for each of these because I don't have any A's in there yet. Just, fiddling around with a couple different combinations for a moment. Okay, so Now we're going to make it a little simpler. Instead of having those numbers in the exponents, we are going to have the rounding on the different sides. But what we'll do is something like the sum of their squares or difference of their squares. This is sort of like creating mutated circle equations in a way, although I'm not putting an A in it there. Ooh, this is already looking pretty neat. Ooh, look at this one. I didn't even finish making it, but look at this. That's crazy. Whoa. A lot going on there. So, to finish making it, whoa, what happened there for a moment? That looked really crazy for a second. Look at that. Okay. Then with the squared. Oh, they don't like that. Oh, that's because the same thing. There's when the sine is bigger than the tangent. What about when the secant's bigger? Getting some planets. So, now, let's throw an A somewhere in here. So, we'll put an A on the X over there, and an A on the Y over there. And these are different values of A. Here it looks... Whoa! What was that? Okay. Here, we have more chaotic looking, and as I get here, we sort of see this shape in it. You see this shape forming? Whoa! Even though this is just a glitch from Desmos, it looks like it's like rising out of this portal. But yeah, that's them having a hard time looking at the scale down there. To zoom in a bit, we can see what it looks like a bit more precisely. For parts of it, there are still like the fractally nature where you can't really zoom in far enough to get all of it because that would be infinitely far. I think they lost the ability to show the bumpiness when I'm that close. Because I'd be more surprised if the bumpiness ended. Now, here we can see that you can use straight lines to make curved things. So, that one's neat. What happens when a little simpler than tangents, we make some of them sines? Oh, not anes, sines. Ooh, that one has a neat shape to it. What will happen when we change A? Parts of it are growing, but other parts of it are changing. Here it hit like a square-like thing. When A is 0, we get this quite square-like pattern. Here, it quickly mutates. We get these cool, like, figurines. Look at this shape. This shape is like an interesting statue. This is like an interesting shrine to whatever that thing is. I like these little discs when there's just like a little chunk somewhere. So, that's one scale of it. So, this one's pretty neat. That was just one of them being sines. What if they're both sines? Ooh, getting some cool things. We see these plus signs combining and forming strange things. At this stage, they look sort of like square things that got rounded. Not rounded in terms of the rounding function we're doing. This is what I'm talking about. That got rounder, like in terms of shape-wise. But when we go over here, it's almost more like round things that got kind of square-ized. Think about when you think. We're halfway between roundness and squareness in this journey. If we can have squircles, which are square circles, can we have squusplines, or whatever you'd call a plus sign, but square? Well, apparently we can. And whoa. So, that is what this fella looks like. And now let's try some different combinations where we're going to make the two sides a little more different than each other. This time we're going to put A's on both of these and neither of these. And we're also going to turn that one to multiplication instead. This is like circles radiating strange energy. And now drawing that energy back in to form new layers. this kind of planetary feeling. Like it feels like here is sort of like the sun expelling energy. Or like here feels like Saturn's rings forming. So now I think over here we're going to try mostly complicating the other side. And here I'm going to take out these squareds and just leave us with sine of xy. And over here we'll do more variations, such as throwing some of this into a denominator of a fraction. Whoa, that did something. So now this is one of the ones that freezes for a while. This one's like permafrozen. This one just looks like this. Oh, that's because I canceled out my a's. I'm being dumb. I don't have anything special around this to make it different than just this being a divided by a included. I have to put something special around one of them to make it work. Like that. This looks like a very fancy part of some item of clothing. Maybe like a bow tie. And here we're being tailors, stretching the... Wait, do tailors make clothes? Yeah, they make suits and stuff. That's what it is. Or are they the ones who make... What's the name of the one that makes shoes? A cobbler? And this one, at first it kind of just seems like it's growing based on the middle, but then the other bits we see are sliding more with the growth, and then it merges at a certain point. It seems to touch around 3.6 when we're there. And now let's look at a slightly bigger scale. That's all sort of just like a small thing that... Whoa! A small thing that's happening for most of the time, but this one starts to get a little bigger. Now it's looking more like eyes. Oh, now it has this spiky bit in the middle. It's like a little windmill. There's a windmill getting wind energy. Okay. So, that one's already pretty wacky, but I was already planning on putting one in the bottom, too. And we've gotten this. This has not only this crazy windmill bow tie thing, but it also has these little island-like shapes that are their own little thing. And I like when the graphs do this, when we get little islands that are disconnected but look different than each other. Then we can sort of pretend, and it's not even really pretending, it's more just a metaphorical, or just the graph version of this. But we are sort of sailing through an ocean and exploring what's happening in that ocean. Here, they get to a point where maybe they're all connected. Do they all connect to the next one? Or does that stop? Oh, it stops. There's a big gap when this one stopped. They were all connected up till this big gap. So, full of surprises. Now, let's look at one of these first islands, just because this one already is pretty interesting. This island has like a top hat and two things on its side. So, let's now try, of course, substituting some other of our trig functions before we move on. Whenever we have a good clump of an equation here, we might as well try a few things with it. And there's that one. Here's if they're both secants. And you'll notice that there's sort of three go-tos I have with the trig functions I try. And it's because they resemble different types of things. Other ones are more similar looking. Sines look kind of like cosines a lot of the time. And so I often do sines and tangents, and then secants end up looking a bit different than those two. So I'll do those sometimes. And sometimes I'll throw in the ones that are hyperbolic ones. But before we do that, let's look at this and appreciate how we get this weird pattern of all these little, but not microscopic, like countable amount of things before it ends and starts another stripe. And the ones in the middle are more circular, and then they get kind of smushed. They become triangle-like at times. All right, there's pretty nice. And let me just read a few comments while I fiddle around with the next few. So thank you for all the people noting things. Someone said it reminds them of fractals. Although it doesn't have the self-similar nature of many fractals, it does have the nature where zooming in on something retains complexity, and there are layers you could zoom in on eternally. So it is quite fractally. And somebody said they'd laugh if the Mona Lisa appeared. That would be pretty crazy. I get it on one setting. It lets me go to 2.1 something else for a second. I'm like, whoa. And then I can't find it again. You know, it would be funny, but in a darker way. Something happens like that while the stream glitches and none of you see it. And I'm like, I swear, guys, while the stream was glitched, it looked just like the Mona Lisa. Okay. Someone is wondering why so many ordered structures appear. Do they have any applications or meanings? They have many meanings in terms of math, in terms of showing like, well, when we combine things like this, it's very unpredictable, yet full of patterns of where there are the things and where there's the gaps. As far as like, would this be helpful in an engineering project or something? Who knows? Because all things that end up being used for technology, or at least most of them, began with mathematical or engineering type ideas that were more just experiments. And so who knows what types of things that are mathematically relevant will become relevant to day-to-day life. But I certainly think that it is, and it's not something that's been explored much, so it's something I have to give an opinion on more than a fact, but I think that if this was investigated more, it would have many cool mathematical applications. And I just think it's really cool. I think it's just something that is fun to do. If I didn't do live streams, I would still do this on my own, just playing around with it. So now, I kept forgetting to change the one on the outside. But that one we'll keep a little simpler. The other one I mentioned that I try sometimes is the hyperbolic ones. Like, or no, it's that. Here's hyperbolic sign. And we got another windmill. What about hyperbolic secant? Well, this one seems like it would be a really boring graph from out here. You're like, that looks boring. Wait a minute, what's that? Wait a minute, it's infinitely dense down here. But it's kind of only interesting in that little zone. I mean, compared to some other options. So, ooh, that was interesting when we just had secant too. Get that little squircle right there, or squoval, because it's not quite a square. It would have been a rectangle. So, oh no, squoval, oval's already a thing. A squectangle. This is a squectangle. Somebody asked if I can keep A without the trig functions. Well, if I don't have the mini trig functions here and here, and I put A on top and bottom, it cancels. Like A over A would just make that part 1. So it'd just be x squared over y squared. That's what I accidentally did a minute ago. And I was like, why isn't it changing? Why isn't A doing anything? So I need something to change them. I could also, even if I'm just like +1, that would change it enough that it is no longer just canceling out the A. A does something, because the A doesn't quite just cancel out. Or I could say times Y. And we get this shard of a universe. But nope, this was one of the ones where it canceled. That we can't do that. I forgot that if I only multiply, it'll still cancel. So, wrong example. Anyway, we'll just put A on the... Oh, here's what we'll do. We'll multiply A on the top and we'll add it on the bottom. Ooh, see, now these plus sign-like things are shifting down into irregularity quite quickly. Here, if you look at it, even though it's partially the glitching, just the way they're tilted looks like 3D. Doesn't this look in a way like this is like going uphill at a steep thing, and this is going over a little curve of something, and now it's sort of going downhill a bit? So it has a almost optical illusion-like feel. And here is our center. All right, now, let's think of some other options. And I think for a moment, I'm going to get rid of the fraction part of it. We're just going to try adding a few things. Well, nope. What we're going to do is we're going to try one bit subtracted by another similar bit. Or let's put this back, x to the y, and then we're going to subtract y to the x, but it's going to be in this thing this time. And now it's only in one quadrant, unfortunately. So, okay, actually, we'll just replace these with squares for now. Uh-oh. There we go. Now, this is simpler. Oh, and I didn't have an A anywhere. So, these are simpler than they were before. We might end up putting the fraction back if we don't get anything as interesting with this right here. But you see what I mean about the optical illusion vibe? This sort of looks like I'm like stretching a fabric back and forth. All right. Someone has a recommendation for a graph, so I will try that one. Or somebody said to subtract that. I'm not sure what you meant to subtract that from. Leave a little clearer, because I've done a bunch in a row. I don't know which one that was a response to. Leave a comment with the full equation you want instead of just subtracting that from something, and then I will try it. So, back to this, though, for a moment. Well, what happens if we put the A out here instead and just hide the A over there? Well, no, rounding the multiplying of A won't be as interesting. We'll put the A outside these for a moment again. Now, what are some other things we can combine here? Well, I think we should just try similar combinations to before, but what I'm going to try this time that's a little different is we're going to have two fractions. One is going to be sine of x over sine of y. And we're going to subtract sine of a times y divided by sine of a times x. It's mostly the inverse of that, but I threw the a's in. So, well, maybe we should have the a's on the one that's not subtracting it. There we go. And here we get some new glitchy fabrics. Whenever it looks kind of grid-like, I like to imagine that you somehow design a board game around this, where sort of like a chess board, like bishops got to stay on their color. You somehow have some rule here, where this is the board. Like, you can hop a certain amount at a time, but something about the color of the regions matters. Design a game around one of these. Somebody? I've been doing a lot of games because I convinced myself that it's all worthwhile because I'm taking notes for an episode I'll make about it someday. But the other day when I did mathematical games and I showed one called Star Battle, that's one of my favorites. Well, I found other websites they're on that have ones with more stars. So, I've been doing really big versions or really hard versions of the Star Battle puzzles. So, I'll come back to those at some point, but those have been reminding me of grids because they are what you could call a grid puzzle, sort of like Sudoku. Now, here we have an interesting pattern. We sort of get, like on some animation shows, it can either be really cheap looking or done for purposeful surreal effect. Some backgrounds, even if the item is moving, just have a steady background, like the item's almost showing a window to some other wallpaper or something. This is sort of like that, because we get these things leaking outward like this wallpaper shifting, but then it like vanishes. Although we could also think of these lines as sort of going through a warping machine. Whenever one of the shapes or lines touches one of those edges, they sort of warp. And this one's interesting too, because we can sort of see this like maze being drawn there, which, like, if I make it just equal for this, we can see this maze that is sort of like a map. And then we get more when we put the inequality, but it's even interesting just at this maze-like state where like some bits of it like look like it could be a maze, like I have to go around. If you zoom in, some of these fill back in. It might have had a missing point right there that they want to show at any level. But you gotta like dodge around here in the maze. Uh-oh, dead end. What about up here? Okay, hopefully this path takes me to my end, not this way. So you see it's a straight up maze. Here I got some forks. Which one do I take? Oh, either of these forks can lead to the same place. All right. Somebody asked, would it be interesting to include the golden ratio in any of these? Perhaps if we're going to raise something to a power, like instead of to the second power, we could go to the golden ratio power or something. However, if we just multiply something by it or use it as a term, it will be basically like a single value of a here, so it's not going to show as much diversity as being able to slide through a bunch of a's. We would maybe get like interesting coordinates that occurred, like it might pass through certain interesting rational or irrational points. But as far as like looking pretty crazy, the golden ratio won't help us as much as messing with variables such as x, y, or my a slider, because, for example, rounding the golden ratio would just be 2. So, and today's theme is rounding. Here, look, you got islands. You got one type of maze here, and here a different type of maze forms. Maybe you have to solve this maze as it changes, and if a wall hits you, you lose. This looks like a video game, then. I'm not even a big video gamer, but I would play that. All right, now, well, I would play it for like 2 minutes, probably, and then get bored. We'll see. I don't know about we'll see, actually. Maybe we'll see. Okay, so let's put the inequality back as we continue our experiments, because the inequality gives us cool colorations. And in fact, you know what we're going to do? Here's what we'll do. I'm going to simplify this a little bit. We don't need all of this in here. We're just going to make this one just y over x, as opposed to all the signs being involved. And what we're going to try is cloning this, copying it down here. And we're going to put it and the clone and a few clones together. We're going to do one clone that's tangents, one clone, and we'll do it for all. Of course, the mixes would create many possible clones, the combos, but we'll stick with different, distinct ones for now. Due to being trig functions related to circles and stuff, they are still going to sometimes overlap at very specific points, or all dodge certain spots that remain white or stuff. Now here we get something interesting. We get like this dense world down here that starts forming gaps, and here a sparse world that starts getting somewhat dense as we go along here. It's forming this strange network of things with our different colors. And we have an a in there, so this is just one value. This is just when we're at negative 7.2 for a. So as we mutate this, we will see what happens. Do these things stay in sync? At what times do any of the colors seem to have something to do with each other? Now, what we'll try to make them a little more similar, we're going to make them combos. So this one is going to be sine over secant is greater than tangent. There could be 6 different ways to combine these like this, but I guess I will just do 3 of them. Secant over tangent and sine. And so now I'm using one of each, but we're going to have them in different arrangements. Okay, now let's see, again, not only just the cool shape, but can we notice times where these seem independent or related? And can we notice anything fixed? Any patterns like grid-like shapes that either remain purely there or that change in a predictable way? Other things are quite unpredictable, like that this would be separate right there. We could also note the interesting things about these white zones being the spots where none of these hold. Now, to make this a little simpler, here's what we're going to do. I'm going to get rid of one of the clones, and over here, we're going to take that out. We'll just do rounding of x times y over there. And this will simplify things a bit. Don't worry, we will complexify it again. Oh, sorry. I did see the other graph in the comments. I only look at the chat like every once in a while, and then I catch up on all the chat because I don't want to be staring at it the whole time. Otherwise, it throws me off my game of ranting. So I'll try your suggestion now that I noticed that. We had a suggestion which was tangent of x squared. It's by Maynard Trendle, plus the tangent of y squared minus -1 to the power of tangent x times y. And do they need me to say that it's all equal to y or something? Yeah, so I'm not seeing anything there. What's going wrong here? Did I do this correctly? Let me know what's going wrong here. So I don't see it. So yeah, let me know if I'm doing something wrong there. For now, to jump back to these ones that we've been doing, what we're going to do to simplify it is we're just going to have two combos that are going to play together. One is going to be one operation over another, and then that operation over that. Like, we're just going to flip which operation we have where with those. And now we're going to be able to see a little clearer two graphs that are in conjunction. Like, we could see this shape seems to always stay within its red square. So there we have shrinking and growing strange little bumps. Some things seem unrelated almost, like the fact that that red dot is at that point. Other things seem quite connected. Actually, no, the red thing there does seem more consistent now that we zoom further, and we see the red things becoming more and more like circles centered around a specific spot. However, the circles do break their pattern too. They get their tops chopped off, and then who knows what happens next. So, going back here, that was if I did secants over sines. What if the sines become tangents? Now, what will these graphs do together? This one's a little simpler, but still pretty cool looking. Now, what about if I try, what's next? The sine and tangent was a combo we hadn't tried yet. This one, we get this lightning, like, jagged thing here. If you're really close, you think that they're doing the same line, but then you're like, wait a minute, are those lines going different? Wait a minute, those aren't the same slope. They're just really similar slopes. And then, wait, here, once again, I was about to say, oh, hey, then it tucks exactly into it. Then I remembered, wait a minute, I just said that if you hadn't looked at the last one with enough detail, you would have thought that it went straight, but it didn't. So does this one actually go straight? I think so. Hard to tell. Then we get that back again. Are these exactly the same line right there? I think that line is identical. This one just looked identical if we were at a certain scale. Right there. If I was right here, it would look pretty like the same line. In fact, it would look like a boring graph right here. We're like, okay, we divided it into 8 quadrants and colored them in, great. But nope. Craziness. So, we get these grid-like patterns. And here, this one, I like noting what they look like. This one looks sort of like an hourglass in the middle. Now, what'll happen if we try some of those hyperbolic ones? These, whoa, this is interesting. We go up on these spiky paths that seem to just end, but they don't actually end. They just get really thin. When they get thin enough on a certain scale, the graph's like, can't show it anymore. But, because if they showed all the thin stuff, some of the graphs would just look like almost completely filled in at certain points. But that one goes up right there. Here, this one chops through right there. They're sort of like these weird reverse parabola thingies, but spiky versions of them. And it's funny that they look similar to parabolas, because I don't have a squared anywhere in here. What if they were both hyperbolic? And hyperbolic trig functions are similar. They're using similar rules to trig, but instead of a circle it being based on hyperbolas. Yeah, this is one of the ones where it's like close to on, but actually off, and then spikes in a way that looks exactly on. Now, this is extra weird because this not only looks like they line up exactly, which I think it does in this case, but it's curved. It's not even a line. That thing has some curve to it. Now here, they separate, though. This time it jumped off, and red now was doing its own thing. And its own thing was approaching that line. Okay, so that's a pretty simple state, but I forgot that we have A as a slider, so we can always change them. All right, now the hyperbolics are cool and all, but I think we can do better stuff than that. Now, what we'll do to mix it up a bit is actually throw in some squareds, because if it looked like a parabola even without the squareds, well, maybe we'll get some more cool almost curves. Curves that got rounded until they weren't round. So, you see how things like that look like a curve, but we zoom in and we're like, although the weird thing about some of these is it is technically curved sections. But are they all? Like, that one looks completely straight, but maybe it's curving the other way? I would need a ruler. But they look curved, and they are little sections that sometimes are straight and sometimes are curved, but have these jagged corners. They have discontinuous sections. So, well, and that's different than the discontinuous sections. Those are, well, and it's even hard to tell what touches and doesn't, and when the slope changes or not, because when you zoom in, you see more stuff on some of these. All right, now, this is very fun. Since it's been an hour, I need to run inside very briefly, just for about, I'll try and actually make it like 2 minutes this time, like I often say it'll be. I'll try and actually make it 2 minutes, and what we'll do when I come back, first we'll just go back to a classic one here and play it. We can watch the animation, or you can watch it while I run inside. When I come back, we're going to try some 3D graphs. We're going to try putting a few of these equations into Desmos's beta version of their 3D graphing or calculator. So here is a little loop of these things, and that made it go way too fast to show us the interesting stuff. So we can go like that. Let's see if it allows less steps or smaller steps, and we're going to make the speed really slow. Okay, and we'll make it different than this because we kind of just saw this. We'll do x over y on these instead of y over x. Well, we'll do one of each. Okay, so I will be back soon, and we'll try some 3D graphs. All right, folks, I am back. And before we try 3D graphs for a minute, I do want to try one more experiment I realized. There's one more crazy thing we can throw in, and that is the factorial. Now, remember, as we showed in, I think the last time we did graph streams, I think was the one about factorials, we showed that they do graph in between whole numbers for factorials. So they're using basically a version of the gamma function, probably a version of the gamma function slid over. It's complicated, and I haven't made an episode about that yet, but basically the gamma function, particularly when slid over a little, shows the factorials, but also shows in between values in a way that makes sense. It's obviously not the main definition of the factorial of something like multiply all the integers up through something, or even the combinatorics version of defining factorials of how many ways of arranging a certain amount of items doesn't make sense for a fractional amount of items or a negative amount. But some things like this, there's only really one, or sometimes multiple, but one main one, or sometimes only one graph that can fit it and retain certain properties. And the gamma function works well for that. Here, they're just not showing all the spikes. It gets zoop, zoop, like up and down. It's flying. It flies up to the sky, flies up from the earth. Down from the sky, up from the earth. And must connect somewhere on the other end. And now we need to try seeing what it looks like rounded first. So if I round factorials, we get this. This weird glitch thing. That zone is quite weird, where it appears vertical until you zoom in. Like, why does that appear vertical? That's pretty crazy. So, I guess it is, and just jumps over and then stops. Now, what happens if we round y being rounded x factorial? We get a spiky version of the gamma function thing. And now, let's try filling it in, just because inequalities are better. And, I mean, not better, but they look cooler usually here. And maybe they are better, because we saw that sometimes they reveal hidden things, like these stripes here. Now, let's try a little mix before we move on. What happens if I try the trig things and the factorial? And my rounding. And we're going to make this xy and y times x factorial. Whoa. What about y factorial times x factorial? Whoa. These are pretty wacky. We'll try more of this combination of... it's a triple combo. Trig functions, factorials, and rounding. We'll try more of the triple combo another day, because I do want to try some things similar to this, rounding trig functions, on their 3D thing. So we're going to jump here, and let me real quick read our comments while I drag these points around. And I'll open the 3D graphing calculator. Well, and this one looks cool too. We'll try their geometry thing another day. This looks fun to explore. And here's another version of their like geometry or a 3D thing. But where's just the 3D graphing calculator? There we go. So, this one is trickier because we can't see 3D, so we're looking at an angle of it, you know, the 2D look at the 3D item from a certain angle, and that's why they need a cube for it to go in. Otherwise, you know, graphing things, a lot of them would go past the edges and blot out the whole screen in a way. To make most graphs digestible here, they got to cut them off in this cube. So, when I zoom in, I'm still, you know, retained in the cube. Maybe they'll give me a way to change cube sizes later. It looks like this is just them testing it out, but it works pretty good so far. Now, reading our comments real quick. Let's see. Lots of great ones. Thank you to everyone for some thoughts and comments. And can't really reply to all of you right now, but some pretty awesome stuff. And somebody notes they changed the OEIS interface. That's strange. I'll have to look at that. I'm not sure if you mean the interface just for creating notes on it, because you say you've published things on there, which is cool, or if you just mean its general view. Let me just see real quick if it looks different. Is it .org or .com? Org. Did they change anything I'll notice about it? Right here it looks similar to me, but maybe I'll notice some differences when I poke around on it more. This is an excellent website, and it will be a recurring stream topic, although a less frequent one as well. We've done before is finding cool types of sequences through here. Now, it'll also show up in several future episode topics of mine. As one mini note before we jump into this, make sure that you are tuned in to my main combo class channel as well, where I put my main episodes and where I'm working on the official grade -2 finale before we move to grade -3. It'll be a whole long documentary-ish look at the creation of grade -1 and a lot of crazy stuff that has happened behind the scenes that you didn't know about. And so that will be coming out. I'm not sure when, because I'm working on it, and it may be long, and it will be quite cinematic-ish. So that will come out when it's ready to come out on the Combo Class channel, and the last episode was sort of the mathematical finale of the grade. But I do have many bonus videos for this channel as well in store. In fact, I've begun posting bonus videos and shorts again on this channel, and there will be a lot more to come. I have actually filmed 3 more bonus videos that aren't out on this channel yet. Now, here, let's see what happens when we just graph something. This is sine of x plus sine of y plus sine of z equaling 1. And they're getting cut off at the edges, but really they're like all these connected shapes. And that's pretty neat. And if I had squared them and thrown in an a instead of a 1, we get the version in 3D of that really cool combo classic I mentioned before. It's hard to see right here, but this is a 3D version of our combo classic. Okay. Now, anyways, what we were mostly looking at was rounding. So let's see some simple things to start. What does it look like if I have rounded x plus y equals z? How do I get back to my main realm? How do I get back to centered? Okay. Rounded x plus y equals z. We see these two little like zigzags flying through space only. So, what if I say rounded x times y is z? Well, now they're sort of in planes only, but they're doing interesting things. They're forming these walls with little gaps. Now, let's get everything going on both sides. So what I'm going to do is rounded x, get rid of you, and rounded x plus y plus z equaling rounded x times y times z. Now we get something kind of simple, but kind of strange as well. Sort of pixelated version of this apartment building. Now, let's try getting a little more interesting. It got interesting when we did, like I mentioned in the title, our combination of trig functions, which are related to an... Oh, this is, you know, core to today's live stream, I just realized, is that dichotomy of the two types of rounding, because trig functions inherently do make round-looking stuff. They're related to circles. And rounding of this sort does the other thing. So we're getting both of them today. Here we're getting a strange surface. I don't think it's able to display it all perfectly. Let's see what happens when I put them all on one side and just have an a on the other side. Well, when a is 1.4, we get that. And that is all that's going on right there. This graph does not have a lot going on, unless it's taking a while to load. But what happens when I separate these into their own roundings? We're going to do that, and we're going to add one for the other two variables. So now we have rounded sine of each of them. And we are seeing when we have to do greater than or equal maybe to see what's going on. when it's greater than or equal to... Yeah, that's what it was. Remember, greater than or equal can hide stuff. Now we get this strange array of things that involves plus sign shapes, like we saw before. These plus signs don't have as much space to mutate in what we're looking at. Maybe if I zoom out a bit. Oh, well, now it gets hard to see anything. Uh-oh. Oh, maybe I can see stuff. This side's just blotted out. Here we got some holes in it. It's a interesting cage. Or maybe this is the apartment building from afar. This is the outside of an apartment building with windows. Doesn't it look kind of like that? Now, let's make this more interesting again. Get me back to an interesting realm. Either it's going to take me a minute to get comfortable with their 3D one, which I've only used a few times, or perhaps they will evolve some functions in the non-beta testing version. Oh, and from Maynard Trendle, there's a $5 donation. That's very nice and awesome. Thank you so much. You know, I get some money from ad revenue, but at this stage of combo class, we don't make a ton of money, and it does take money to hire people to help me film and get props and stuff. So anyone who makes donations to the streams or supports on Patreon, much thanks, such as Maynard Trendle here. And somebody said I should try x cubed plus y cubed equals z cubed and see if that's a sphere. Now, if I want to, you're close to the right track, but I'm actually not going to need to use cubes. I just need to use squares with 3 variables. So I just need to say x squared plus y squared plus z squared equals a, and make a positive, and get to the right scale. There's my sphere. I knew you were hiding there. So here we have our sphere, and if I want to grow it or shrink it, I change my a. So it is interesting that when we get to the 3rd dimension, we are not going to cubed. We are just going to 3 different variables. Now, if I added a 4th axis and had, you know, plus another thing squared equals a, it sort of would be a hypercubes equation. And remember in 2D, when we were looking through slices of an a with 2 variables going, it was like hinting at 3D. Well, here, it's in a way hinting at cross-sections of a 4D thing. A 4D hypersphere in this case. These are the slices of your 4D orange. Okay, so that's pretty neat. Somebody noted the Menger sponge, or however that's pronounced, which is a really cool fractal. Let's just take a look at that thing they noted. Cool fractal shape. So there's a fractal curve after 4 iterations. Basically, each iteration you are cutting out the middle 9th of a section and then treating each of those remaining 8 as they get a bit cut out, although a 3D version of that. Let's see how they describe it. The way they describe it is a 3D generalization of the 1D Cantor set. Which this will probably need an episode. It's where you cut out the middle third of a line, then you cut out the middle thirds of those, or of a line segment, then the middle thirds of those, the middle thirds of those, and so on. This actually reminds me of this times table behind me. This times table, I needed 9 columns to go from, this is for a bonus video. I needed 9 columns to go from 0 through 8. And can you see the times table? Let me see. Is it too dark to even see? Here, I'll turn this up for a sec. So, this is for a bonus video coming out on the channel soon that I already filmed. I needed a times table that went up to at least 8, and I wanted zeros on it. So I needed 9 columns. To make 9 columns, you know the easiest way to do that is to split something into 3s, split into thirds, and then split each of those into thirds. And so, reminiscent of this. And the Cantor set will someday get an episode because although it's like, okay, what's the big deal? You cut out the middle third, then the middle third, then the middle third. It has a lot of really cool properties. And this is a 3D generalization of that. And the 2D Sierpinski carpet. Now, the one that'll get extra attention in an episode is the one known as the Sierpinski triangle, because this is, for one, related to modular arithmetic, for two, related to Pascal's triangle, and it's related to the combination of those in ways. For three is just a really cool fractal. And for four, showed up in one of my personal investigations of one of the coolest things I've ever discovered that I haven't made an episode about yet, because I need a really good visualization of it. So I need to work with someone who knows how to program and then graphic design what they programmed a little bit. So that is called my pond forest sequences. Just wait till you see my pond forest sequences. Anyway, that's a little tangent side thing. Let's go back to our graphing calculator. Somebody asked if I could do a really simple equation a while ago. So I would say right now, if we want a really simple equation, the sphere kind of qualifies, but to get even simpler, we could say, like, what's x plus y plus z going to look like? And this is a plane. It's getting cut off, but these are the times when x plus y plus z equals 1, when each of those coordinates adds up to it. So there's a pretty simple one. Now, I could even say like x equals 1, but then I just get this line. We don't really need 3D for that. Like, I can do a 2D equation and just have it on this thing, but then I might as well have been in 2D. So, various thoughts. Somebody also noted I should learn to program. At some point, I will learn basic mathematical programming so I can test more of my ideas further, but I don't think I'm ever going to get really deep into programming. I have a lot of hobbies and interests already, and so there are certain things like programming that I will never become a master at because I have books to write and music to record and, you know, things to prove in math and a lot of side quests. So, somebody said they don't know what happens in the stream, but they did start integrals this week and they're awesome. Yeah, think about, if you rewatch any of this stream or my other graph streams, how integrals could maybe come into play with analyzing them. And a lot of other cool thoughts. Oh, somebody said pond forest, like a pawn shop. It is a pond and a forest, like a little bit of water, because that's what it resembled, what the sequences did. But, no, I don't get these necessarily from pawn shops. I don't think, like, fully, but I get a lot of them from thrift stores, which are, I guess you could say, a version of a pawn shop. So I do get these from thrift stores and yard sales a lot of the time and stuff like that. You know, if I'm going to be using stopped clocks, I always tell people I don't need it to work. Like, I'll ask random people sometimes, just like, hey, do you have any broken clocks you got to get rid of? So, and then sometimes people are like, I have this working clock, but you could have it. And then I have to give them the little speech where I'm like, I will accept this clock under certain terms and conditions, which are, you're okay with watching it shatter at some point, and it will live a reduced lifespan. However, it will probably have its reduced lifespan documented and maybe help capture people's attention towards education. So it will be more historic than sitting on a shelf somewhere, but it's not going to last as long as sitting on a shelf somewhere. Do you still want to give me the clock? So anyway, thank you to also somebody who noted just that they were blessed by the algorithm with this channel. Yes, who knows how or why people get shown my videos on their page if they've never seen it before. The algorithm is something not fully known to humans, and in fact not fully known to any human, because it has many robotic components to it that I don't know if a single human would be able to summarize. So we're going to just try a little bit more rounding, and let's see what happens when we put them to different powers. X gets no power, y gets a squared, and z gets a cubed. And we're just going to make this equal to a. So why does that one have bigger parentheses than that one? What's going on? Oh, because that one didn't need a squared, I guess. The bigger parentheses made me think there were more of them, like they were outer bracketing, but I think it's just to fit the two. That reminds me of this really funny math meme I saw. Maybe this will show up in the next time we do a live stream about math memes, where it was a picture of part of a book where there was an equation, and the 2 was also at the bottom, like how a little number, if it wasn't math but was after a sentence, it would imply a footnote, a small 2, like this is the second footnote on either this page or chapter or book. And it had a footnote that's like, this 2 should also be treated as an exponent and not just a footnote. And if you have a lot of exponents in your book, you probably don't want to have that gag and keep doing it. But if you only have one exponent in your book, it's a brilliant gag to do. So maybe we'll do another live stream about funny math memes at some point before long. There will also be one about making beats before long, mathematically, like we've done once or twice, and other topics that we like to recur, such as weird Wikipedia, which we are still getting through our unusual Wikipedia articles, and that will likely be the next stream, will be another batch of very strange Wikipedia articles. Something went wrong. What went wrong? They won't even tell me what went wrong? Oh! I told you the inequalities hide stuff. It's crazy. It wasn't even, not even blank. It wasn't even just not working. Now the inequality works. Okay, here we got an interesting realm. What does it look like at different sizes? Strange. We had one of our variables to the first power, one to the second power, and one to the third power. Let's kick this up a notch. We're going to do a second power, a third power, and a fourth power. Uh-oh, not the 34th power. Okay. So, these are some interesting shapes. They're harder to see in 3D. While the 3D is really cool, I don't really like always being stuck in the cube. Let's see if we can uncube it. No, this is just to orient the cube. Okay, what can we do? What does this do? Whoa! Why would I want my cube to be conical? Wait, now it's like, looks like it's tilted that way. It's like conical that way. What? I want the cube to be normal. What, normal is just like there or something? That's weird. What do these do? Oh, that's kind of neat to view it. It's kind of cool. We'll keep it like that for a sec. But I do have to say, I don't know if it's their beta version or just how 3D graphs are harder to view. I kind of miss the 2D graphs already. I like trying things on the 3D graphs, but I don't know. Now let's try one thing though. One type of graph that we haven't tried 3D yet, that if it looks cool, we'll save it for another live stream, but I want to at least quickly experiment, is what happens when I do polar coordinates. So remember, that's 2D, and how do I extend it to 3D? What is that? Oh, that just made it go up. Now, is there a way to... No, I can't put it in terms of X, Y, and Z. Yeah, so I don't know if I can do polar coordinates in a 3D way. I don't know much about the sphere version of that. So, still neat for a second. Anyway, we'll try it a little bit with the... Oh, the cube's all tilted now. This is weird. It looks like the wrong shape or something. Okay. We're going to wrap it up back on the 2D graphs. I'll experiment with the 3D graphs a little more on my own and make something cool happen with them. But for now, we're going to go back to our 2D graphs. And I think we will be wrapping it up before long, probably in 5 or 10 minutes, because I want to work on some other stuff. However, leave any last thoughts or comments as I explore a few final graphs. Let's take one of them that looked neat already, such as this. And this one was when we started throwing factorials into the mix. And what happens when I throw it on different sides? Whoa, this is like a crazy painting. This looks like someone splattered paint together and made a weird modern art painting. Look at this craziness. Now, this is so crazy, I even just want to see for a second a simpler version of this without the trig at all. Just with rounding different ones being factorials. This is when rounding x times y factorial is bigger or equal than rounding y times x factorial. We get this. Looks like a checkerboardish pattern happening at times here in a weird way, but not quite. It's almost like an optical illusion that when you look at this real quick, like when I'm going, like if I'm over here and you look at this, it looks checkerboard-like. But then you're like, wait a minute, there's not actually like, there's barely any cells that go back and forth red to white in a consistent way. It's more that we can see these shapes getting cut off right there that makes these two almost look like neighboring checkerboard cells. But it's not really checkerboard. Like those are two filled in ones mostly in a row. Those are two white ones mostly in a row. So that's already pretty cool. What if I add instead of multiply? Sometimes it's actually cool to have a mix of addition and multiplication because then you get a combo. So here we're getting a kind of checkerboardy thing for a moment. And then we get these spikes like stalagmites. We get a little fern right there. So now let's try. We're going to go as deep as we can for the finale of this. We will have a fraction, and we'll start with sine instead of secant. And here, we're going to experiment with a few. We'll put okay, I'm going to delete all the old ones. And we'll keep the a. We're going to put the a somewhere. A will be on the one that doesn't have the factorial. And now we're going to do some mutated version of this over here. We are going to instead have the y up there and the x down there. And just beginning with that, we get this thing, which we can now edit with our a. Now, to have a few colors at once and make it extra wild, what we'll do is try another combination of this, which is the one where, well, we're going to try a few combinations. One is going to be that the factorial is on the bottom. We're basically just going to switch these. Ax and y factorial, and ay and x factorial. Another one would be, what if the factorial side gets the a too? So now the a's are going to be on the factorial side. And now we're going to try the final clone of that pattern, which will be having that but flipped with the factorial on top. Wait, so I kind of did these backwards the way I substituted these. Let me see if this is consistent. We have x factorial over ay turns to ax over y factorial. Then here, this should turn to, I don't know. We'll do this. Close enough. One of them might have, be a backward version of what it was looking for, but they're still interlinked. We can see that these graphs sort of play together and create shapes together with their different colors. I like that little zone and this zone. Now, we're going to go out and change our A. Warning. Ooh, look at this stuff down here. It's like this, we're exploring a mine and we found a bunch of crystals. Whoa. So, now let's change our a bit, because it's just for one value. This is when a happens to be 0.9. What happens when a is 1? So here, you see at 1, these are touching at a bunch of spots. We get this chain of diamond-like things, but we can see if we zoom in enough, at least this one has a bit of a curve there. Perhaps they all have some curve in them, not sure. Hard to tell at some scales. Now here, we get some more spots where things touch each other, or spots where they don't. And let's explore this mine a little bit. Now, that's just at 1. So what happens when we change this a bit? Well, we're going to get this whole mutated wild pattern. I'm going to shrink this a bit so we get a little more watching room. And we're going to edit RA. And we get these crazy different combo landscapes. Okay, let's make these a little simpler because with 4 colors, there's kind of a little too much going on here maybe. So what we're going to do is just, instead of having these flipped sides, we're just going to make this rounding XY on that side. Because I think with 4 colors, we can go a little simpler. All right, what are these ones going to do? Wait, but now it's different because these all have X on top and that one has the X on the bottom. So we want to do that. Strange stuff growing down here. Here it becomes grid-like. It's rectangles. But whoa, this grid has some chaos in it. This looks like a weird detector of something, like it detected weird earthquake shaking or something. And here we get a lot of chaos. Once again, this is just at 1 value of A that happens to be negative 0.2 right now. Okay, also, by the way, I'm going to wrap up the live stream quite soon. But if anyone really wants, I'm thinking of dropping one of the bonus videos that's already uploaded and basically ready to put out right after the stream. So if anyone wants a short bonus video to come out tonight, leave a comment and I will consider it. Otherwise, it'll probably come out maybe tomorrow morning, either tonight or tomorrow morning. But if anyone really wants to see a bonus video right after the stream, let me know and I'll consider it. And to all the people with random cool comments, thank you. And someone's saying they play 4D Snake, which that sounds cool. Snake's that one where you wind around, try not to hit your tail and try and eat the dots without hitting your tail. But yeah, 4D Snake sounds interesting. You can play things like 4D Tic-Tac-Toe. That will come up when we make an episode about Tic-Tac-Toe. Believe it or not, you can get a lot of math out of some relatively simple things. And some examples of episode topics I will make someday. Whole long episodes on my combo class channel will include tic-tac-toe and rock, paper, scissors. And some things like that that you may think are trivial if you don't dive really deep into their structure and their possible variations and such. So, here we get a little random blip hanging out right there. Get some waves and stuff. And this is just when A is 2.9. And just when the equations are right here. Let's try flipping these around a bit. Now, someone mentioned I should make a game, or maybe it was to another commenter, but they said I should make a game. And I would consider designing games at some point, but I don't think I would be the programmer behind them. So someday I could imagine being the designer behind a game. Like, I like even designing inventory puzzles that are based on logical combinations, or designing maps potentially that are maze-like. So that could be fun. Oh, and we got Maynard Trendle again, gave another $5 saying to drop the video. He wants to see a bonus video right after the live stream. All right, we're going to do it. Right after the live stream ends, within 10 minutes, there will be a bonus video out on this channel. Probably within 5 minutes, but definitely within 10 minutes of when I end the stream, we'll have a bonus video out on this channel. It's kind of short. It's a 6-minute one, and it's going to be about a random sounding topic, but I find it interesting, relatively simple, but I was going to drop it as a short. I decided, I couldn't get it in a minute. I kept filming it, and it kept being a little over a minute, and you got to make them under a minute to be a short. So I was like, I'm not even saying all the stuff I want to be able to say about this, and it's not under a minute. I'm going to make a bonus video and give myself more time to explain things a bit more and a little more, philosophy leading into it and such. It's a pretty short random one, but like I said, it's one of 3 bonus videos that I've already filmed to put out on this channel since we're close to the end of grade -2. While I work on my long main finale episode, I'm going through a bunch of my notes and just seeing random extensions to topics that I talked about, but I didn't talk about the extension to, or random things that I just feel like would be a fun bonus video to tuck into this grade. For the shorts lovers, I also have a couple shorts ready to go, and a couple that I put out recently as well. So, somebody said they're very interested in the thing I said earlier about generalization of Sierpinski triangles against different simplices. How do those relate to Pascal's triangle and modular arithmetic? I'm glad you're very interested, but I will be explaining those in full episodes. Don't worry, they will be in the upcoming grade -3 because we'll do a lot of 3-based things, including talking about triangles. And so they're at least in grade -3, there will be an episode about the connection between Pascal's triangle, modular arithmetic, and Sierpinski's triangle. And then we'll also just talk about some generalizations of those to different dimensions and that. It'll be a later episode, possibly in grade -3, that I will discuss my pond forest investigations that could be seen as a generalization of Pascal's triangle in a way. Now, somebody said adjusting the parameters of rock, paper, scissors is very interesting. And not only that, but rock, paper, scissors has strategy because you're playing humans who are not perfect random number generators. And just as a simple example of how you could, possibly use strategy, if you were playing enough games in a row, maybe someone would try and switch it up a lot of the time from one throw to another and then do that one a couple times in a row. Or maybe if they were doing it a bunch of times in a row, they would keep at it up until a certain point. But maybe sometimes are less likely. Maybe it's less likely, for example, that they would throw something exactly 4 times in a row compared to 3 or 5. You'd have to look at different layers of philosophy. Now, for that reason, I read a book about rock, paper, scissors when I was in middle school about strategy, and I would play it with my friends all the time, and even just out of 2, best out of 3 matches, like who wins 2, I guess it was, I forget if it was first to win 2 or first to win 3. I think it was first to win 2, I guess, and it could be more games because you can tie on them. I found optimal throws that I did find psychologically worked better. And so rock, paper, scissors has tournaments and stuff. People, maybe you can look into the opponent's eyes and say, oh, that person just threw a scissors, and I can see from the way they act, they're going to throw something different the next time. So I'll throw whatever I know. I'll throw paper, because if they don't throw a scissors again, they won't beat me. So that one's interesting. And thank you to everyone just leaving fun random comments. Somebody said one of my vids is their Slack status at work. That I don't even know what Slack status exactly means. I assume it plays when you're not doing something or another. In any case, whatever a Slack status is, that's awesome. I love when my videos show up different places. It's my favorite thought to imagine, oh, someday this video might play in some classroom or another, or, oh, this was a video maybe some people showed their friend or whatever. Those are very awesome thoughts to me. I love the way that we have spread this far just in our -2 grades so far, or about -1.9 amount of grades so far, because I'm still wrapping it up. And one of the next steps of my finale that I'm filming will be sleeping in the classroom in a tent. And last grade I did it for one night. Might do it for, or maybe I did it for a few nights last grade. I forgot. Because I slept in the front yard at least for a few nights, and I slept back here for at least one night. And this time I'm going to definitely sleep back here for at least a few nights and see what weird wild animals and stuff we might encounter. And one of the things for the finale that I already did was take a field trip to the good old sundial that came up a few times in grade -1. So I think I'm going to wrap up now and double check that my bonus video looks all right, the bit I pre-uploaded of it, and upload it within a couple minutes, within about 5 minutes of the stream ending. So, like I said, it's just a short random one, but I'll have another bonus video or short all lined up that pretty much every day of at least the next week we'll have either a short, a bonus video, and the shorts don't always go to subscriber feeds, although the last few I accidentally clicked them over even though I didn't intend to. Sometimes those I just assume if you like them, you'll see them on the shorts tab, or just check my shorts tab once in a while. But sometimes they go to the subscriptions. There will be bonus videos, shorts, or live streams pretty much every day of the next week because I have a good amount of content lined up. And I hope you all enjoy the pretty random 6-minute one tonight. It's kind of funny the degree to which it will seem random, the concept of what we're doing, but it's a very simple example of something that has been a useful mathematical technique throughout history. So, hope to see y'all on the bonus video. Leave a comment on that if you came from the stream, and leave comments in general if you have any requests for what topics we do next, whether you're looking forward to our next unusual Wikipedia articles, our next graph streams, our next looking at math memes, our next one where we look at the OEIS, the Online Encyclopedia of Integer Sequences, or what. And I love all of you. Thank you so much for joining me in my combo world, and I believe I will wrap that up.